Before 1800, when Herschel infrared rays, the visible spectrum was an isolated phenomenon. In 1801, Young discovered diffraction, proving the wave nature of light. In 1873, Maxwell published his comprehensive wave theory. In 1887, Hertz discovered radio waves. Röntgen's discovery of X-rays extended our knowledge of the spectrum to the very short wavelengths beyond ultraviolet. With this discovery, he provided a new, powerful method of investigation. The rapid advance of modern physics began on the evening of November the 8th, 1895. At the Physical Institute of Würzburg, Röntgen had been studying a paper published by Leonard on the absorption of cathode rays. Leonard had measured the transparency of metals to cathode rays by using a paper indicator coated with fluorescent material. Röntgen repeated the experiment. He placed a shield over a Crookes tube and used a paper coated with barium platinocyanide. As Leonard had reported, the cathode rays caused fluorescence to a distance of 120 centimeters. But suddenly, Röntgen noticed something fluorescing nearly 10 feet away. A letter A, also painted with barium platinocyanide. This was far beyond the range of cathode rays in air, yet there was clearly some connection with the tube. He immediately began experiments to test the nature of this new phenomenon. Röntgen concluded that he had discovered a new kind of ray, and for weeks concentrated his attention on experiments, observing their penetration through a 1,000-page book, through his own hand, and through sheets of various metals. A few days after the discovery, he brought his wife down from their apartment in the Institute and made the first X-ray photograph of a human hand. Röntgen's paper on a new kind of ray was published early in January 1896, and within weeks his results had been confirmed throughout the world by doctors and physicists who took these radiographs of hands. The value of the new photography for medicine was realized immediately by doctors. Many adapted their electrotherapy apparatus for X-ray work. This apparatus, now in the Science Museum, was built in 1896 by a 17-year-old medical student, later Dr. Russell Reynolds, who became a famous radiologist. Radiographic diagnosis was soon accepted as an essential tool for surgery in peace and war. Not without harmful effects. Many radiographers suffered X-ray burns. Some lost fingers and hands. But these very accidents led to the use of X-rays in therapeutic treatment. From early days, attempts were made to provide protection. Now, safety measures are strictly observed. Radiography can be carried out by young women without fear of ill effects. The rays which produced this photograph passed easily through flesh and bone. But we know that light rays, too, pass through solids, such as this Aztec crystal skull. Are X-rays and light so very different? Röntgen showed that his X-rays were caused by the bombardment of the walls of the tube by the cathode rays. He proved that X-rays travel in straight lines, that their intensity is inversely proportional to the square of the distance, in the same way as light, and that they cannot be deflected by a magnetic field. He put forward the theory that they were waves, though he was unable to demonstrate refraction or diffraction of X-rays. The interference patterns shown when light is diffracted through Young's slits are an accepted proof of the wave nature of light. Could X-rays be diffracted? In 1912, von Laue suggested that X-rays might be diffracted if the regular arrangement of atoms in a crystal was used as a diffraction grating. This proved to be so. The Lowy patterns are further evidence that X-rays are electromagnetic waves. In 1913, W.H. Bragg used crystal diffraction to measure the wavelengths of X-rays, placing them in the electromagnetic spectrum with wavelengths shorter than ultraviolet light. In the last 160 years, our knowledge of the spectrum has been extended far beyond the narrow band of visible light. Röntgen's discovery of X-rays was a major contribution to this knowledge. X-rays occur naturally in radioactive elements, but an X-ray tube provides a more easily controlled source. This early X-ray tube contained rarefied gas. Gas-filled tubes operate in a similar way to gas discharge tubes. A stream of electrons is built up by ionization of the gas atoms and by ion bombardment of the cathode. In 1913, Dr. Coolidge in USA designed this high vacuum tube in which the stream of electrons comes from a heated cathode. All modern tubes, like this one, work by a similar principle. The X-ray tube has two essential electrodes: the cathode, source of free electrons, and the anode, the target for the stream of bombarding electrons and the source of X-rays. The cathode consists of a wire filament inside a metal tube. To release electrons, the filament is heated by passing through it an electric current at low voltage. When an electrical potential is applied between the cathode, negative, and the anode, positive, the free electrons, being negatively charged particles, are attracted towards the anode. The tube around the filament, also at negative potential, helps to focus the electrons into a beam. When the potential between cathode and anode is made very high, electrons strike the anode with great energy, and X-rays are produced. What is happening at the anode? This is a simplified diagram of atoms on the surface of the anode, each atom having a nucleus and electrons which revolve around the nucleus in orbits at various levels. The nucleus is charged positively, the electrons negatively, so that between them there is a powerful force field which is balanced by the kinetic forces of the electrons. Electrons from the cathode arrive at the anode with energy provided by the voltage across the tube. Some are stopped or slowed down by collisions with the force fields. Like any moving body, when it slows down or stops, an electron must give up energy. It is this energy which becomes X-rays. An electron which strikes a force field head-on gives up all its energy in one photon. Another may make glancing collisions with several force fields and give up part of its energy in each photon. Quantum theory states that the quantity of energy given up in each photon determines the wavelength. When an electron makes a head-on collision, the photon emitted contains all the energy from that electron and so is of short wavelength. The electron which makes glancing collisions gives up energy in several photons of longer wavelengths. No electron can have more energy than the voltage across the tube, so the electron which gives up all its energy in one photon produces the shortest wavelength possible with the given voltage. The spectrum of X-rays produced with a given voltage has therefore a short wavelength limit, X-rays produced in single head-on collisions, and a band of wavelengths extending down into the ultraviolet, produced in glancing collisions. This is known as the continuous or white X-ray band, by analogy with the broad spectrum of white light. A curve showing total energy radiated looks like this. The intensity rises sharply from the short wavelength limit and falls away gradually towards longer wavelengths. In addition to the white X-ray band, the spectrum from an X-ray tube contains narrow line spectra. These are the lines from a tungsten anode. They represent very high energy. What causes the line spectra? A clue to their origin is found by altering the voltage applied to the tube. A higher voltage increases the energy with which the electrons strike the anode. The energy given up in collisions is greater, and the resulting photons of X-rays, having more energy, are of shorter wavelength. As a result, the radiations from the tube show a shift of the short wavelength limit and of the whole white band to shorter wavelengths. But the line spectra stay where they were. Their wavelengths are not altered by an increase of energy in the electrons striking the anode. This is because line spectra are not produced in the same way as the white band X-rays, but by radiations from deep within the atom. The radiations causing line spectra come from the electron orbits near the nucleus. These are named the K level, the L level, the M level, and so on. Normally, the number of electrons in orbits is such that their combined energy balances the nuclear attraction. So the force field is balanced. However, if a cathode electron penetrates the force field and strikes a K-level electron with sufficient, it can knock it right out of the atom. This leaves a vacancy in the K shell, and the force field becomes unbalanced. An L-level electron jumps to fill the vacancy, then an M-level electron to fill this vacancy, and so on until the balance is restored. When an electron jumps from one orbit to another, it must give up energy, just as a satellite does when it falls towards the Earth. The electron gives up energy in the form of X-rays. In a given element, the energy difference between K and L orbits is always the same. Therefore, the amount of energy given up in such a jump is always the same. And since energy determines wavelength, the wavelengths of the K, L, and M lines in the spectrum are fixed for the element. If the anode is of different metal, different lines appear. These are called, therefore, the characteristic X-ray line spectra for the element. Von Laue's hypothesis on the diffraction of X-rays by a crystal lattice has led to an entirely new field of research, X-ray crystallography. This is Bragg's original X-ray spectrometer. It is similar to an optical spectrometer, but uses X-rays instead of light. The X-rays are passed through slits to select a parallel beam. The beam strikes the crystal where it is diffracted. The diffracted rays pass to an ionization chamber, which is adjustable, where their intensity is measured by means of an electroscope. The Bragg method of X-ray spectroscopy depends on the diffraction of X-rays by the atoms arranged in the crystal lattice. X-rays are selected from one of the line spectra so that they are all of one wavelength. The rays are directed onto the atoms in the crystal and are reflected by scattering from each individual atom. At this specific angle, the reflected wavefronts will all be in phase, like the incident wavefronts. This results in constructive interference. But if the reflected wavefronts are selected at a different angle, like this, they will be out of phase and destructive interference will occur between atoms in a crystal. In the same year, using the X-ray spectrometer, Moseley was able to demonstrate the relation between atomic weight and atomic number, to fill in the periodic table of elements, and to forecast the discovery of 3 elements then unknown. With the X-ray spectrometer, W.H. Bragg provided confirmation of quantum theory and laid the foundations for wave mechanics. It has contributed to our knowledge of the structure of complex molecules and provided a precise definition of the electrical charge on one electron. For industry, X-rays provide a non-destructive testing method. Products like these transformers are radiographed to show whether they have been assembled properly. One has a correct, the other an incorrect oil level. This steel plate has been welded across its length. An X-ray shows faults in the weld which might lead to fracture. A casting may appear sound from the outside, but an X-ray reveals bubbles inside the metal. At London Airport, an X-ray unit is available night and day to make emergency or routine examinations of aircraft. Parts which are known to be heavily stressed, like this wing section, are repeatedly X-rayed for fatigue defects. This X-ray shows that no strain had occurred. The first application of X-rays was in medicine, and this is still their widest use. The skilled radiologist can diagnose internal conditions with far greater certainty than can be got from external examination. Recently, a new instrument, the X-ray image intensifier, has provided doctors with a brilliant optical picture with low-intensity dose for the patient. Combined with cine-radiography, this makes possible permanent records on film of the functioning of internal parts of the body. Röntgen's X-rays have become a versatile instrument of science. We live in an ocean of electromagnetic waves, and properly interpreted, they can give us a picture of our surroundings far beyond the power of the human eye. It is up to us to learn to interpret them. X-rays are produced when electrons from the cathode strike the anode and give up the energy imparted to them by the voltage across the tube. When many electrons are making head-on or glancing collisions with the force fields of atoms in the anode, the white band or continuous spectrum of X-rays is radiated. In head-on collisions, electrons give up all their energy in one photon and produce the shortest wavelength, corresponding to the voltage applied to the tube. This accounts for the short wavelength limit. Each element, when bombarded with electrons, produces characteristic lines in the X-ray spectrum which identify the element. These lines represent X-rays radiated when orbital electrons jump from one level in the atom to another, lower energy level, and so give up specific quanta of energy. Since the quantum of energy determines the wavelength, these lines have their fixed places in the spectrum. And X-rays take their place in the total spectrum of electromagnetic waves, with wavelengths shorter than those of ultraviolet light.